Welcome to today's edition of ROHDE SCHWARZ 35. My name is Markus Lerner. I'm a market segment manager for RF and microwave component test. The subject for today is phase noise and its effects in DDS-based architectures. Why is phase noise an important topic in digital modulation systems? When data is transmitted using digital modulation, it is modulated on a carrier using higher order modulations in order to be more efficient. Typically, the higher the order of modulation, the more constellation points we have and the more denser they are. We have here an example of a 16 QAM with no phase noise. We see the behavior is on the left side. Each modulation point is perfectly shown and can be seen with data on it. As soon as we introduce to the system phase noise, we see that the data is not really anymore perfectly aligned to the constellation points, but it's moving around in a circle structure, which you can see even more on the right side where there is more phase noise involved. The more phase noise, the wider the range of the variations. And if the phase noise is actually too high, there will be bit error rates because the signal looks more on the receiver side that it would come from a different constellation point. On the other side, in radar applications, when we are looking at the target, at the signal coming back from the target, and we have high power signal being sent out with a certain phase noise on it, it could easily mask the target. It spreads out the clutter signal and masks this way the response. Typically, correlation mechanisms are used in order to overcome that issue and still gather information from the target. If there is phase noise involved, correlation is not possible anymore. So what is phase noise? When we look at an ideal signal, an ideal CW signal, it is basically a sinusoidal wave. We see this very nicely in the time domain, where it's a typical sinusoidal behavior over time. And when we look at the signal in the frequency domain on the right side, it is a discrete line. When we look at a real signal where there is some noise, some fluctuations involved, we see two components of fluctuations. One is the amplitude fluctuation and the other one is the phase fluctuation. Those are overlapping to the ideal sinusoidal signal as we see in the calculation formula, but also on the graphs. On the sinusoidal signal, it's not really in time domain anymore a perfect sinusoidal, but there is some distortion. When we look at the frequency domain, we see not anymore the discrete line, but we see that it's kind of spreading out in the frequency domain. And on top, when we see this over time, the level variation would also be not constant anymore. So what we see in phase noise is basically an unintentional phase modulation, which makes the signal spread out in the frequency domain. You could also say that when you compare in the time domain, phase noise and jitter are like the equivalent in both worlds. When you look at phase noise on a one point in time for a dedicated signal, you can see in the green line, which is the wanted ideal signal as a phasor shown. And when you overlap a real world environment, meaning you have amplitude noise and phase noise, you see a variation of the phasor in length based on the amplitude noise and its angle based on phase noise. So the measured point at a certain time is different than the ideal constellation point. When we look on the phasor there is always on a certain signal thermal noise. Thermal noise, or KTB noise, has equal components of amplitude noise and phase noise. So this is a similar relationship. When you see a certain variation of the phasor more on the length axis, the noise is dominated by amplitude noise. On the other side, if it's more like the angle which is varying, the noise is dominated by phase noise. When we have a look at the digital transmission system, as we see here as a picture from an oscilloscope where we are looking at an eye diagram, typically you say the eye diagram must be large enough so that we have a good and stable transmission. It is typically limited by jitter, as it kind of narrows my eye opening. The more the jitter, the wider the crossing of the signal lines are. Thus, the eye opening gets smaller. So this is a direct relationship between jitter, phase noise, and the possibility to include high data rates with low bit error rates. For phase noise, there is a new definition from the IEEE organization. It basically looks at the spectral density of phase fluctuations. From the older days, there is a more traditional, more intuitive definition. Phase noise is defined as the relationship of the power measured at a certain offset from the carrier in a certain bandwidth, typically 1 Hz bandwidth, in relative to the carrier. It takes a difference of the different power levels at the offset to the carrier level. That is also why the unit which is used for phase noise is dBc per Hertz. In oscillators, there are different causes for phase noise, and they can be clustered in different sections when we look at the phase noise plot. Obviously, really far out, we are looking more at white noise, at noise floor, which is caused by amplifier, by broadband output noise. And the closer we get in, there are different contributors to the noise, as we see here on the table. In a real world scenario, those contributors are all present at any time, but based on the design and the type of the oscillator, there is a different weight and a different contribution factor of each of those noise factors. How can we correlate phase noise and jitter? Because in a DDS-based system, when we're looking for a system which is based on a D2A converter, for example, jitter is a standard function. And when we look at this formula here, we see that jitter is actually a function of phase noise, and it's integrating phase noise over a certain bandwidth in units of seconds. So when you would do any measurements of a phase noise and you do an integration from a certain start offset to a stop offset, you get automatically with this formula a jitter number. What this already shows is that based on the start and stop offset, you have a big influence on the different jitter numbers. So when comparing jitter performance of an oscillator, you always want to look at the start offset and stop offset, over which range is it integrated. If those do not match, you cannot really compare the numbers. The benefit of using a phase noise measurement system compared to an oscilloscope is that it gives a very high sensitivity. Jitter measurements can be done all the way down to 10 femtoseconds. On top, the phase noise plot gives you more information about the sources of the jitter, like if there are discrete lines from dedicated sources. It gives you more information on random and deterministic jitter effects. This is hard when you just measure the width of the crossing on an oscilloscope compared to the eye opening as we saw before. The downside is that only clocks can be measured, not random data streams. So how can this be done with a dedicated test instrument? At first you would say, well, what I want to measure is a certain power level at an offset from the carrier. I can do this with a spectrum analyzer. Very true. And there are also additional marker functions available on today's spectrum analyzers which correct for the ratios of the used filters compared to the 1 Hz measurement bandwidth so that you get a real phase noise reading. But on the other side, is this really a correct technique? And how accurate is it? The first answer is yes, the technique is perfectly valid. Well, otherwise, such a marker, such a phase noise marker would not be available. But this method has some limitations. On one side, the own noise contribution of the analyzer. On the other side, you have a minimum offset which you can do, and especially for some demanding radar applications, you might be interested in offsets which are even smaller than 1 Hz compared to the carrier, and this cannot be really measured in a mode with a spectrum analyzer. So we need to come up with a different approach. So what we are looking at is a dedicated phase noise analyzer. What it does is it takes the input signal from the DUT, from the oscillator, and transfers it, compares it with a phase detector to a reference source. So this converts phase fluctuations into voltage fluctuations. The benefit is that only the reference source adds a signal to the signal's phase noise, and that the main power, the main carrier energy from the device under test is removed by the phase detector and the following low pass filter. So what we are seeing and providing to the next stages, instead of taking the complete sum signal with the carrier and the offset signals, like in a standard signal analyzer, standard spectrum analyzer, we just do provide the phase fluctuations as voltage fluctuations and provide these towards the baseband section, where then we do the evaluation of the data. This gives us much more sensitivity and opens up to measure further down than with a standard spectrum analyzer approach. On top, the phase detector also offers and gives us for free the removal of the AM noise, as we saw before. And with the phase detector, it allows us to measure offsets closer than 1 Hz. Now, what we've seen so far is that the reference is the only contributor and the only thing which still adds some additional noise in this scenario. But in an ideal world, we want to get rid of the influence from the reference source. Obviously, you want to take a low noise source, but even the best low noise source still has some noise. but you only want to measure the noise which comes from your device under test. So we have to find a way to get rid of the noise contribution of the reference. What we do is we basically double the measurement approach. So we take the same path a second time and apply the signal from the DUT not only to one channel, but to two different channels here. And both of them are built up in exactly the same way, with phase detector, with its own reference source, low pass filter, LNA, etc. So what we get is a signal from both with the main contributor noise from the DUT, but also with the noise contribution from each reference. What we use then is a mathematical process called correlation, where we are able to take out the common parts of both signal change. So with correlation, we are able to basically get rid of the noise which is different on the upper channel and the lower channel, and only keep the noise which is common, and that is the noise from our DUT. So in this way, we can basically reduce the noise from reference 1 and reference 2. Depending on how many correlation runs we are doing, we are able to improve our reference noise suppression. As a rule of thumb, you get about 10 dB for 100 cross correlations, and you get about 20 dB for 10,000 cross correlations. Let's have a real example. We are taking one DUT with correlation and without cross correlation. The upper curve in blue is the measurement without cross correlation. Is this really the true performance? It doesn't really look like it. When we apply cross correlation, we see a plot which is below it, which shows us the true performance of the DUT. And while increasing the number of cross correlations, we are able to push down the sensitivity of our phase noise test system. On the downside, the higher the cross correlation, it also costs more time. So what is the latest enhancement to overcome some of those limiting factors? On one side was the time requirement, but on the other side, how can we make more efficient phase mesh noise measurements, not only on CW signals, but also, for example, on pulsed signals, or can get additive residual phase noise measurements. For this, there is a new invention here, which we call a digital phase demodulator. Instead of the classic approach with the phase detector, so where we put in correlation, where we put in contrast to each other the phase of the DUT signal versus the reference signal and measure those. No, we are taking here an IQ demodulator basically. So it's a standard demodulator as we know it from our digital modulation systems, which is used also to measure phase noise. In order to be able to run again cross correlation to improve our sensitivity, we are also in this approach offering two separate passes with two references and allow here to also do again cross correlation. The benefit already is that this approach gives us a much faster measurement using, again, very high sensitive and very clean references. But the overall process with the IQ demodulator and the digital processing gives us a faster response. And to give you an example, assuming the same sensitivity, the same accuracy, we get a measurement time down by a factor of 10, for example. In an example here, we measure a high sensitivity measurement from 1 Hz offset to 1 MHz, which is a very common range. And this is done in less than 30 seconds. The digital approach also gives us a very wide range of offset capabilities. And for an example here, it offers from 10 millihertz all the way out to 1 gigahertz. An additional benefit we can get out of the information from the digital demodulation and the cross-correlation information, it is providing you also some guard band between its own noise floor, which is shown here in gray, towards the phase noise measurement, which is shown here in yellow. So if there is always a certain gap in between, you know that you're not measuring the analyzer, but really measuring the device under test. While in the classic phase detector, AM part is basically taken out automatically by the phase detector. And if you want to measure both, if you want to have an information not only about phase noise, but also about amplitude noise, you would need a separate measurement setup. The digital concept here gives us the benefit of providing information at the same time for amplitude noise as well as for phase noise. And both of them can be shown in parallel in the phase noise test setup. Now let's have a look at residual phase noise. What is the difference? In a standard phase noise measurement, there is a signal coming into the phase noise analyzer, and it's just measuring the phase noise from all of the signal which comes in. So it measures the overall one port signal from a DOT, which could be CW or pulsed. When we look at residual or additive phase noise, typically what we want to know is how much is added by an additional two-port device. So when we put into the system, for example, an amplifier, a mixer, up-down converter, how much does those components contribute to the phase noise? The classic approach with a one-port measurement setup measures the total sum which comes in. So it measures the sum of the noise from the source and from the DOT. For a dedicated residual phase noise measurement, we just want to see the effect or the added noise from the DOT. So we somehow need to be able to kind of separate between the two. We can do this in a simple way with our phase noise analyzer by using the low noise synthesizer from the instrument and take this as the driver into our device under test. So instead of using an external source, we are using the low noise source, which is used inside of the analyzer for providing a CW signal towards the different IQ mixers for the demodulation. And based on the concept, it basically takes out the noise of the low noise synthesizer and is able to measure the phase noise addition of the device under test. So let's take this one step forward, and how does this translate to a DDS? As an example, we want to have a look at using a 16-bit D2A converter, which we're going to use as a CW source. So you can program those to create a signal out. You program this on the digital side with a input frequency with an input signal or directly from the component itself, and it provides an RF output up to 6 GHz in this example. Obviously, to drive it, you need a clock signal. Unfortunately, any noise from the clock is directly translated to the RF output. But again, what we want to understand here is not the overall phase noise of the DDS plus the clock plus the reference clock, but we want just to understand the phase noise contribution from the DDS system. That is our goal. Okay, let's see how we can do this. In a typical measurement, what you would see is when you do the measurement on the phase noise analyzer, you see the absolute phase noise including everything. You cannot separate between the two devices. When we taking a simple approach at first, non-frequency converting device. So assuming the clock would be the same as the RF output, we could use the concept as discussed before. We could use the low noise synthesizer as an LO and drive with this the clock of the DDS, or in this example any DOT. And based on the concept that the low noise synthesizer is driving the signal and is also the same signal which is provided to the IQ mixers to down convert the input signals where we have a contribution from the device under test and its low noise and its own synthesizer. Thanks to the IQ demodulation, we are basically taking out the contribution to the noise from the low noise synthesizer. This works when we have exactly the same frequency on the input and output. But when we have different frequencies, which is the common setup for a DDS, for any kind of a synthesizer, we have different frequencies. So that approach does not work. What is able to be done is then to say, okay, let's provide an LO into the phase noise analyzer, which is used to demodulate the signal at the RF frequency compared to the synthesizer, compared to the LO, which is used in this example, for example, as a clock. So how does the setup look like? We take again the phase noise analyzer, take the RF out, the synthesizer out from the internal synthesizer of the phase noise analyzer, take this as the reference for our DOT and provide the signal from the DOT to the RF in. But we need a second DOT. Ideally, we just take this same device just a second time and take this as a translator from the RF out, from the LO, towards the RF frequency of the DOT. So both of those devices are working exactly the same way with the same setup, with the same transmission. In order to measure then the phase noise, we see here on the right side the block diagram how the different signals move along inside of the instrument. We see obviously the RF input coming from our device under test, which is sent to both sides of the IQ demodulators for the phase measurements. And as LO, we have the contribution, we have the signals which come from our so-called golden DOT, or the second DOT, however you want to call it. If the two signals would be perfectly in line with each other, we would have the same benefit as before, and the effect would basically go away from those phase contributions from the second golden DOT. Unfortunately, it's also a real-world DOT, and the effects do not go away. So what we are trying to see is, can we use any kind of cross correlation to get rid of those? In this example here, where we have exactly used the same DUT for channel 1 and channel 2, both of them have the same correlation. So we cannot use cross correlation in order to just take out the effect of our RF signal. This is why we need to move one step further and use not only one golden, but two golden DUTs for the two different channels. The setup is exactly the same as before, just that we take two translators for channel 1 as separate and for channel 2 as separate. This way we have then, as a result from our IQ mixer, the signal coming from our device under test, and on the other side, separate from the two different golden DUTs which translate the RF signal as clock towards the measurement frequency of the DUT, which is used to demodulate. And as those are different, we can now use on the result of the two different channels correlation mechanisms in order to basically calculate out, filter out, so to say, just the common thing, and this is our noise contribution from the DUT which we want to measure. In this way, we can use one instrument, one phase noise analyzer, together with multiple DUTs to measure the phase noise contribution of the device under test and take out any effect from clocks. So it's really a measurement of the residual phase noise as added by a DDS. One thing which comes on top is a finding while going through all this measurement approach is that, well, if you measure phase noise on a DDS, it's not only important to look at the quality of the clock and how can you get rid of the clock effect, but on top, the power supply has a pretty significant influence. What we see here is a difference between using a standard power supply, a standard regulator, and another one to use an improved regulator, a really good one. So when you just look at the measurement plot from the red curve to the light blue, the benefit here, or the variance between those two, is nothing else than just using an improved regulator. So this also comes into play when you do measurements on a DDS system. Or if you want to apply a DDS system, you do not only have to worry about the clock, but really about also the performance of and the cleanness of my power supply. And here is a picture of a complete measurement as it was shown at an exhibition with this setup using a phase noise analyzer on the left side, which is called a Rohde Schwarz FSWP. And we are using an SMA 100B as a clock reference towards the different synthesizers, and take 3 different synthesizers which are stacked above the instrument on the right side to have one as a real measurement device and 2 additional to create the LOs which are used inside of the digital demodulator of the phase noise analyzer.